Welcome to the instructional video explaining about the workings of your built piano. In this video, you are going to learn how the piano you've built works. We will look at each component in the circuit and understand in general what its function is and what it does. Towards the end of this video, we will also discuss how to expand your new electronics hobby from here on, and where to look for more information about the subjects covered in this video. For more information about this piano kit, visit www.xoftc.com. Before we can understand how any device works, we need to know what its purpose is. In the case of our piano, it has two purposes. 1. To be able to produce sound. 2. To be able to change the frequency of the sound produced so that we can create different sounds. Now that we know exactly what our device does, it is time to learn how it works by addressing each one of its purposes. Let's start by having a look at the first purpose of our piano device, which is to be able to produce a sound. How is sound produced? The piano device uses one component, which is called a buzzer. A buzzer is basically a smaller and limited version of a speaker. The same speaker that you have in your mobile phone, television, radio, stereo system, laptop, tablets, and many more devices. Our buzzer and a speaker work on the exact same principle, where we have a diaphragm made out of some material, and using electricity, the diaphragm is pushed forward, back, and forth. This pushes the air in front of the diaphragm, and the sound of the air being pushed is what we are hearing. These are called sound waves. To understand this, we will look at an example of a drum. When we hit the drum, we produce a sound. This sound is the result of the air being pushed out of the drum. Buzzers and speakers work on this exact same concept, only instead of having someone that will constantly hit the diaphragm, we use an electronic device that will push the diaphragm back and forth, just like what happens when a drummer hits the drum with his sticks. This electronic device that we are using to push the diaphragm back and forth is called a coil. This way, we can produce very precise movements of the diaphragm, and therefore, we can also produce different kinds of sounds. Now that we understand how sound is produced, it is time to understand how we can control the buzzer in order to produce different sorts of sounds. In our drum example, we learned that when the drummer hits the drum, this causes the diaphragm to push the air forward, and we will hear a sound. Now it's time to see how the frequency of the hits that the drummer does can affect the sound that we are hearing. Frequency is the rate at which something occurs over a period of time. In this case, the rate of hits that the drummer will hit the drum. In this first example, we will hear what it sounds like when the drummer hits the drum once every second. In other words, we will hear what it sounds like when the drummer hits the drum at a frequency rate of 1 Hz. Now let's hear what it sounds like when the drummer hits the drum once every half a second, or in other words, at a frequency rate of 2 Hz. In these two examples, our brain can still capture the gaps between each hit on the drum. Now let's hear what it sounds like when the drummer is hitting the drum at a frequency rate of 20 Hz, which means 20 hits every second. We notice that the sound is taking a more continuous form. Now let's hear what it sounds like when the drummer is hitting the drum at a frequency of 40 Hz, which is 40 hits per second. And we can also hear what 80 Hz sounds like, and also what 160 Hz sound like. Everything you just heard was simply the result of increasing the amounts of times that the drummer hits the drum every second. Some other interesting facts about sound frequencies: a woodpecker will peck the tree and the sound that is produced is around 20 Hz. A housefly beats his wings and will produce a sound at around 300 Hz. When a mosquito beats his wings, the sound that is produced can reach up to 600 Hz. At some point, when a specific sound passes the frequency range that the human ear can capture, we can no longer hear it, but it is still there. That sound range is called ultrasound, and it starts at a frequency of about 20,000 Hz, or in other words, 20 kHz. Now that we know exactly how our buzzer works, how sound is produced, and how different sounds are made using different frequencies, it's time to learn how we can create an electronic device that will act as our drummer and hit the buzzer in order to produce sounds. For that, we look to another unique component in our piano device, and that is the NE555 integrated circuit device, or in short, IC. The NE555 IC is a device which has a specific function in electronics. There are many other types of devices, each with its own unique function. Some are for counting, driving motors, storing information, sound amplification, and even entire miniature computers which can be programmed to carry out multiple tasks. The one thing in common with most of these devices is that they all have input and output pins which we need to connect, and each pin either receives electricity or doesn't receive electricity. The NE555 is just a circuit much like the piano, only that someone else has already designed for us to use in order to produce these timed hits on the buzzer. And in fact, that is why the NE555 is called a timer, because its function is to produce timed units of electricity. If we look into the circuit that makes up the NE555, we can already recognize similar parts that also exist in our piano circuit, like resistors and diodes. The other parts in the circuit are called transistors, and they are also part of the very basic components in electronics. A transistor acts just like a switch, only instead of pushing the switch with the finger, the transistor allows us to push the switch using electricity. Now all that is left for us is to configure the NE555 so that we can define at which frequency we want these units of electricity to come out. When we talk about these timed units of electricity, we are basically talking about on and off. That is why the NE555 is also known as a switching device, because it can produce a signal that switches between on and off repeatedly. Each time that the NE555 gives an on, that means that electricity is going through the coil inside the buzzer, the coil charges, and that pushes the diaphragm forward. And each time that the NE555 does not give an on, or in other words it gives an off, the coil inside the buzzer discharges and causes the diaphragm to return to its original position. Just like with our drummer, he can decide if he will hit the drum harder or softer, faster or slower, and these settings will produce a different tone coming out of the drum, just like you heard earlier. In a similar way, we are configuring the NE555 timer to produce the on and off states faster or slower, or with more on time than off time. This is called a duty cycle. Here is an example of a fictional machine. This machine will fill up bottles of water that move along a conveyor line, ensuring that each bottle gets exactly the same amount of water each time. You can see that the machine receives water from the top. This water fills up a barrel-like structure with a weight at the end, and once the weight of the water exceeds the weight of the barrel will tip over and drain the water into a bottle, and this action repeats for every bottle. If we call every bottle an on and the space between the bottles an off, we get the exact way of what the electronic signal coming out of the NE555 looks like, with its on state and off state. This is called a square wave. Now, if we replace the water with electricity, we start getting a better picture of what these on and off timed units of electricity look like. This principle of producing an on and off signal is what makes everything around you these days work. So exactly how do we configure the NE555 timer? using those basic resistors, capacitors, and diodes. First, let's have a look at the resistor. A resistor is a device that allows us to control how much electricity, or in other words, current, we want to flow through the line. The size of the line is our voltage. In our piano, we use a 9-volt battery. Current, in simplified terms, is the amount of electricity that flows through the line. The resistor's job is to resist this current and limit it on the other side so that we can control exactly how much current we provide to different components in the circuit. Resistors are used overall in electronics, and they are the basic building blocks for every circuit. We can measure different currents, voltages, and resistances using a very basic law in electronics, which is called Ohm's law. We can see that in each circuit, the voltage will be equal to the total resistance multiplied by the current will be equal to the voltage divided by the resistance, and the total resistance will be equal to the voltage divided by the total current. Resistors come in different values which describe how much resistance is placed on the line, and they are measured in units called ohms. To know the exact resistance value of a specific resistor, we can look at the color codes that are printed on it and use a color chart to figure it out. The more ohms a resistor has, the higher resistance it will give, and therefore it will allow for less current to flow through the line. In our bottle filling machine, a resistor will regulate how much water goes into the barrel and how much time it will take the barrel to fill up until it tips over. Next, we will look at the capacitor. A capacitor is a device that will receive electricity, charge up, and then discharge itself. A capacitor can store electricity, but unlike a battery, if we disconnect the power from the capacitor, it will discharge itself. Capacitors, just like resistors, have different values which indicate the amount of charge they can store, and they are measured in farads. A 1 farad capacitor can hold an enormous amount of charge. Therefore, the normal value that are used for capacitors are microfarad, nanofarad, and picofarad. Capacitors have all sorts of usage. In our bottle filling machine, a capacitor will act like the weight tied at the bottom of the barrel. The more charge the capacitor can hold, the heavier the barrel will be, and more time will be required for the barrel to fill up and tip over. However, if we were to use a larger capacitor as a weight at the bottom of the barrel, we can use a lower value resistor to regulate the current flow and allowing more current to come in faster. That way, we can create the same filling rate with different resistors and capacitors values through balancing them accordingly. The NE555 timer in our piano device has a configuration similar to the example of the bottle filling machine. We use the 22 nanofarad capacitor C1 as our weight and the resistors R2 and R3 as our water flow regulators. Another example of usage for capacitors, which we will find in our piano device circuit, is for filtering out a signal. That is the purpose for the capacitor C2, which you find between the NE555 timer and the buzzer. An important thing that you need to remember about capacitors is that some of them are polarized. That means that just like the LED and the diode, they have specific positive and negative leads, and it is very important to connect them the right way. Otherwise, they simply explode. If you are using a polarized capacitor, always make sure to connect them the right way. Both resistors and capacitors can be connected in different setups in order to get different resistance or capacitance values. The two most basic setups are called in series or in parallel. For resistors, if we connect two resistors in series, meaning one after another, we get a resistance value that is the sum of all the resistors in the same series. For example, a 1 kilo ohm resistor in series with a 10 kilo ohm resistor will give a total resistance value of 11 kilo ohms. If we connect them in parallel, we get a different result. For example, a 1 kilo ohm resistor in parallel with a 10 kilo ohm resistor will give a total resistance value of about 900 ohms. For capacitors, it's the same, only the calculations are the other way around. For example, a 100 nanofarad capacitor in parallel with a 22 nanofarad capacitor will give a total capacitance of 122 nanofarads, where if we connect them in series, we will get a total capacitance value of about 18 nanofarads. At this point, we have covered the first purpose of our piano device, and that is to be able to produce a sound. If for a moment we disregard the resistors R4 to R10 and only focus on R2, R3, and the capacitor C1 with our NE555 timer, we have successfully configured it to produce a drum hit, or in other words, a square wave signal at a frequency rate of 262 Hz, exactly according to the manufacturer's instructions in the NE555 user's guide, or in other words, datasheet. This datasheet comes with every type of device that is out there, and it includes all the information you need in order to use a specific device. You probably noticed that between R3 and R2 there is another component. This component is called a diode. A diode is another one of those basic components, and its function is to allow electricity to flow only in one direction and block it if it comes from the opposite direction. It has a positive and a negative lead, and current will always flow from the positive to the negative, but not in reverse. The negative side on a diode is always marked with a line, and whichever side this line is facing, that is the direction in which the current will flow in. In our piano device, the diode does not serve a significant purpose, and the piano will work the same if we just removed it. The only thing it does is prevent the current from flowing back in the opposite direction, as an example. Now it is time to look at the second purpose of our piano device, and that is to be able to change the frequency rate of those on and offs which are hitting the buzzer so that we can produce other frequencies aside from the 262 Hz we have so far. This would be an easy task now that we understand how we are producing sound using the NE555 timer and a buzzer. If we know that R3 and R2 are responsible for deciding the frequency of the signal coming out of the NE555 timer, and we know that this entire configuration is balanced using the two resistors and the capacitor, all that is left now is to replicate this setup using different values in order to produce different frequencies. So how do we go about that? First, we need to understand how exactly the values of the two resistors and the capacitor are calculated in order to produce a specific frequency. For that, we have all kinds of formulas and calculations which again the manufacturer has provided in the NE555 datasheet. You can try calculating these values yourself using pen and paper, but in today's world we have calculators for almost every task that is involved in building electronic circuits. So what we need to find is a calculator. Once we have a calculator, it is time to go at it. We want to achieve the goal of being able to produce different frequencies with minimal changes to the configuration, so we are going to try and make all the changes by replicating R3 only with a different value so that we can get a different output frequency. How do we know which frequency we need to produce for different notes? Once again, we refer to resources that someone else has already compiled for us. And if we look online, we can find a chart that describes all the frequencies of the natural scale of notes. Our piano device has a range of 8 notes from C4 up to C5. This range is called an octave, coming from the word octavus, which is Latin for 8. And indeed, we have 8 notes in our piano, starting with C4 and going through D4, E4, F4, G4, A4, B4, up until C5. This specific range is called the 4th octave. The fifth octave, for example, will range from C5 going through D5, E5, F5, G5, A5, B5, and C6, and it will use a higher frequency range and will have a higher pitch sound than what our piano produces. In the same sense, the third octave, which ranges from C3 up to C4, will use lower frequencies and will have a lower pitch sound than what our piano produces. We already know that the frequency of C4 is 262 Hz, and that means that in order to produce this tone, the NE555 timer will need to produce a on-off signal that will hit the buzzer 262 times every second. Now it's time to look at the frequencies of the rest of the notes and calculate which resistor values we need to use in order for us to get these frequencies. Using our calculator, we can find out that when using C1 capacitor of 22 nanofarads and a R2 resistor of 5 kilo ohms, we will need a R3 resistor with the value of 240 kilo ohms. And this will give us a frequency of around 262 Hz. Our goal now is, without changing R2 or C1 and only adding another separate resistor which we call R4 and has a different value than R3, to produce a different frequency than 262 Hz. When we raise the value of 240 kilo ohms to 250 kilo ohms, we can see that the frequency has dropped from 262 Hz to 252 Hz. And when we lower the value of 240 k ohms to 230 k ohms, we can see that the frequency has increased to 273 Hz. We can see that without changing C1 and R2, we have managed to produce a different frequency. Now we go back to the chart which describes the various frequencies of different notes on different octaves, focus on the next whole note after C4, and see that D4 has a frequency of about 293 Hz. Our goal again is, without changing C1 and R2, reach the frequency of 293 Hz, and using our calculator, we can find out that if we lower the initial 240 k ohm resistance on R3 to 215 k ohm, we get 291 Hz, which at this point is close enough for us. We can always get more accurate results by fine-tuning the resistance values, and a degree of accuracy does play a great deal when it comes to electronics. However, for this example, you will barely notice a difference in the tone between 293 Hz and 291 Hz, unless you have really sharp musical hearing. So we continue for each one of the notes on the fourth octave from C4 up to C5, and for each set of resistors we create its own switch that we can use to close the circuit or open it, and that keeps all the notes separate from each other. For the E4 note, we want to reach a frequency of 330 Hz, and we will use a resistance of 190 kilo ohms. For the F4 note, we want to reach a frequency of 349 Hz, and we will use a resistance of 178 kilo ohms. For the G4 note, we want to reach a frequency of 392 Hz, and we will use a resistance of 157 kilo ohms. For the A4 note, we want to reach a frequency of 440 Hz, and we will use a resistance of 139 kilo ohms. For the B4 note, we want to reach a frequency of 493 Hz, and we will use a resistance of 123 kilo ohms. And finally, for the C5 note, we want to reach a frequency of 523 Hz, and we will use a resistance of 115 kilo ohms. Once you have completed all 8 notes from C4 up to C5, you have successfully finished building your piano. What happens when you press 2 keys at the same time? For that, we need to look back at some resistors theory. When we press 2 keys at the same time, We are basically connecting two different resistance values in a parallel setup, and that will simply produce a different frequency. For example, if we press the C4 and D4 keys together, we will be creating two resistances of 240 kiloohms and 215 kiloohms in parallel, which using our parallel resistance calculator will result in a total resistance of 113 kiloohms, which is not that far from the resistance we use to produce the frequency for C5. So pressing C4 and D4 together will produce almost the same sound as C5, only with a frequency of about 10 Hz higher. Now we know all the basic things about this piano device and how it works. We learned how sound is produced and how we can use electronics to produce it. We also learned how to change the frequency of the sound so that we can produce different sounds, and that about covers it all. The next step would be to talk a little bit about what to do if you want to continue developing your new hobby and where to start from. The best way to continue will be to simply start making other circuits and devices according to other schematics and slowly build up your experience and knowledge. If you have built the piano kit yourself, then by this point, even if you don't know it yet, you have all the knowledge that you need to start building some pretty cool and fun projects all on your own. You learned about the basic components and how to handle them. You learned about the fundamental principles of electronics. You learned how to read an electronic schematic and carry out each step. You learned about the basic operation of the piano and how the components interact with each other. You learned where to find information about different devices. So now it is time to simply do some more building. You can start by continuing on this path of producing different notes and frequencies using what you already have learned by simply adding more keys with other resistors. You can add a fifth octave continuing from C5 up until C6, or you can add a third octave by going from C3 to C4. All that following the same techniques and method that you've seen in this video. This will give you a much broader range of notes to play with, and so you will be able to play more complicated tunes. All that is required is a few extra components like a bigger breadboard, some resistors, a few push buttons, and some wire. If you want a more structured approach, you can purchase an electronics experimental kit, which will guide you through a series of basic circuits and teach you all the fundamentals that this video did not cover, including some other basic parts like transistors, which we mentioned briefly, coils, motors, logic devices, and all sorts of other type capacitors, resistors, and diodes, amongst other components. If you already have ideas that you want to make, you can start by looking for more dedicated projects like how to drive motors or how to use microcontrollers and LCD screens, and in no time you will be making some cool projects of your own, and the internet is packed full with them. The most important thing is that you have patience and will to learn, and that is all that it takes to slowly become an expert. Always remember safety first. And as a beginner, never attempt to deal with anything other than DC power, which comes from batteries. Electronics can be a great fun, but if misused or handled incorrectly, it can hurt you and even kill you. So be careful and have fun. You can find many interesting beginners projects and information on the xoftc.com website and YouTube channel, which includes lists of parts, schematics, and breadboard layouts that will make things easier for you as you become versed in reading schematics and making different circuits. In the description of this video, you will find a link to resources over subjects covered in this video, which will give you more in-depth information, and also links to recommended channels to further broaden your knowledge of electronics. We hope that you enjoyed building this kit and following this video. If you want to continue and follow this channel and other projects at the xoftc domain, then please subscribe. Have fun and thank you for watching.